Today I'll talk about two topics, mainly just to show how can we analyze our experiential data. So the first is the geometric representation of data. So it's like mean, standard deviation. How can we show the data, the distribution of data in MATLAB, covariance matrix, eigen information, and how could we use those in order to predict or interpret the evolvement of our system. Second part would be about information theory. So like Shannon entropy, what is entropy really, what is information, and how can we like measure the information from our, like let's say 500 trials of experiment, and what is Kullback-Leibler divergence, and how could we use that. So let's begin with the geometric representation of data. So let's say we have a set of experiment, like for example we are recording a force data from 500 trials, and we want to see the distribution of these data. So like to say I'll just do the MATLAB code, like we generate a random random number of 500 trials. So F would be F is 500 trials. So like let's say we have a 500 recording of force. We want to see the distribution of this. So we see what is the mean of that. Sorry. So the mean of this force is 0.02, which is just random number. And then the standard deviation. So I would assume that you all know how to compute the mean and standard deviation and what are the variance of the data. So, and how can we plot them? So I'll just plot it using histogram and the fitting of the histogram. So we can see that pops up here. So from 500 trials, I get the mean and then the standard deviation. Okay. So this is basically how you would plot and show your probably result in only one single feature space. So here, let's say we are just recording force over multiple trials.
Because around 55 of these entries have the value of 0.2, something like that.
I'm sorry?
So the tallest column
Yep.
says that around 55 of
Yep.
your readings
Yep.
have this value of.
Yep, exactly. So the mean is around 0.02 roughly. No, the mean. Sorry, yeah, the mean is 0.02.
And how you use the histogram for have a kind of view of how your data is spread or something like that?
You could compare this with multiple, like let's say you have force resulting from multiple variables or multiple parameters, like for example. You can compare this to see how the force evolves. Like let's say the mean changes, the standard deviation spreads or like broaden up.
So does that mean the random number generator is not very random?
That's what I was checking.
This one I generate
okay.
normal distribution.
Okay.
Yeah. Just so it's nice and easy to see.
Because if it was very random, you should have had a more flat sort of.
This is normally distributed.
Yeah. I use this command.
This rand n,
Rand
this
n.
is not rand.
Yeah. So it's like normal distribution.
Yeah, those. So if you did rand, you can show that.
Yeah.
Rand, it is the flat thing. least fit.
So his fit still fit the normal distribution, but it becomes
Yeah.
like this.
But it's a flat thing.
Yeah.
Okay.
So
But-
what does the red curve say in the second and the other figure?
No, it is also trying to fit a normal
Yeah.
distribution
Ah.
to that data.
So but normally I would assume that our data are more or less like Gaussian, normal distributed. Yeah. Okay. So this one only good when we have only one feature space. So like let's say we only measure force from one sensor, for example. So what if we have a multiple sensory sources from one interaction, from one experiment? How could we show this data? And how could we use the information obtained from this data to interpret our result? So let's say we have two sets of data, X and Y, from like sensor X and sensor Y, with the mean of this much and the variance of this much. So I can generate X and Y first, with the mean of 0.2 and Y with this function. Figure 2. So now our data looks like this. So X and Y. So this is the distribution of our data, randomly distributed. What can we tell from this data?
And there's a direction.
Yeah, there's a direction of distribution, right? Which
There's
is
a major direction and a minor direction.
because if we use the same method as we did previously, we'd get the mean and standard deviation of each X and each Y. It does not tell us about the covariance of those two variables. That's why we need to also consider the variation of the covariation of both set of data by computing the covariance, which I will not go through because this one is quite straightforward. This in the covariance matrix, we have the variance of X alone, the variance of Y alone, and the covariance, which are equal to each other. So if you look at the formula, the covariance is 1 over n minus 1 sum of the data point minus mean and the other data point minus mean. So if we swap them around, they can be the same anyway. So we can see what is our covariance matrix in our data. So here is the covariance matrix. So you can see the covariance are the same for X and Y. And this is the variance of X alone, the variance of Y alone. How can we check that this is the variance of X and this is variance of Y?
So you can take the separate standard deviation of VAR.
So if we
You can do VAR directly. Not
VAR.
STD, VAR.
Okay, yeah. Yep. And here's the covariance. So, like, we have covariance matrix now. So this stores information of the variation of our data. How can we extract the information from those metrics?
When you say covariance, what do you actually mean?
The covariance means how the data are spread out in this feature space or eigenspaces.
Okay.
So the covariance matrix tells you how those two are related to each other and in what direction. Okay.
Which could be, I mean, out of two totally separate experiments, or we could just, but that would be meaningless.
Yep, exactly.
Yeah, so if they're unrelated,
Yeah.
the data will be all over the place. So,
Yeah.
right, so if it is covariated,
You
you
will
will
see-
have a kind of a more like dense variation along a line, but which is it can be any orientation, but like more density is there.
Mm.
What is the difference between the variance? I mean, you use the variance and then before you use the standard deviation.
Variance
Variance
is
is square of a standard deviation.
Oh.
Okay.
There's also a little, so the denominator was n minus 1, but sometimes it's n.
when you calculate the mean, it's
Oh, so the
No.
variance
So in the denominator, you use
n minus 1
N
because your the data point at the mean it doesn't add anything to this sum, right? So it is mean minus mean is 0, and then that point is not going to add anything.
So you mean this one I have 1 over n, and this one I have 1 over n minus 1, right?
Yeah.
This one is just to compute the mean.
So in the mean,
Uh-huh.
1 upon n, because like you add all the data points, right?
Yes.
In the variance, you subtract the mean,
Okay.
right?
So you're
subtract,
taking one of the.
taking one out,
Yeah.
right? And then you just take one upon the other.
Okay. So before I move on, any more question about covariance metrics?
You see that command when you said x equals that and then y equals.
Uh-huh.
How come you added x to it? Or
Because I just wanted to have certain shapes.
okay, alright.
I want them to spread along that way. Because otherwise it'd just be symmetric and boring.
Okay.
Well, this is just random numbers.
And we use this in terms of two different parameters and see
How they covariance
how
which
they're
are-
covariant. Okay.
So with this command, what good about this command is that you can specify the standard deviation and the mean of the data that you want to generate. So not like ran n that I used earlier. This one you can tell, okay, so I want mean 0 with standard deviation 0.2, for example.
0 is what?
The mean.
The mean is 0. Okay.
But you see that the real mean is not really exactly 0.
Is there a way of distinguishing where the data you got covariance between two sets of data and just when they are correlated to each other?
If they are correlated, they must be covariance, right? What do you mean by correlated?
The correlation coefficient. So correlation coefficient is calculated from the correlations. Pearson's correlation. So it's called the Pearson's correlation coefficient, which is
I'm not covering.
no, it's an equation, so it's a straightforward.
Okay. So, any more question? Okay.
I believe covariance could be generated in more than 2 dimensions.
Yep.
And hypothetically, it could be n dimensions.
can have as many as you want, like 3-dimensional. Yeah. So now we have only 2-dimensional, 2 feature spaces. How can we get the information out of that covariance matrix? We'll not go through the text. I think you can read it later. So basically, in any matrix, any square matrix, like let's say matrix A, in this case, we can compute the eigenvector and eigenvalues from this relationship. So basically,
So if I go back, so if you divide covariance of diagonal component, sigma xy, right, by sigma xx times sigma yy, that is correlation coefficient.
can you repeat that again?
S12 S12 is the variance, right? But take it's fine. Divided by S11 times S22.
In bracket?
Yeah. No. That S12 is numerator, and the denominator is 11 times S22. Yeah. Square, first one square root.
Square root.
The numerator is square root. The way you are dividing is something. Can you do help CORR? Yeah, CORR. Yeah. That's correlation coefficient.
Ah, okay.
Yeah. And then it will have the equation.
I'll just
Correlation coefficient, CORR, COEF, or doc correlation, yeah. Yeah, CIJ
okay.
divided by square, divided by
Okay.
square root of CIJJ. So it is, if your covariance is high, the correlation coefficient is high.
If
Yeah, it's 0.45. Correlation coefficient is if it is 1, it is on a line. If it is 0, it is a kind of a patch. This the correlation coefficient is a measure of how linearly correlated these things are.
According to the
It's called the Pearson's moment correlation coefficient. Is that right?
Well, according to the lab, it says that returns the matrix of correlation coefficients and the matrix of p-values for testing the hypothesis that there is no relationship between the observed phenomena.
Yeah. Or p-value. So if it is a p-value, if you want to get. Okay.
okay.
Yes.
Okay, so the eigen information. So basically, for any square matrix, there is an eigenvector that for which this relationship holds. Well, lambda is eigenvalue, which we can calculate from this relationship really. Anybody is not familiar with eigeninformation?
I think
Eigen-
it's better to go to basic.
Okay. So, like, let's say if I have.
Everybody familiar? Everybody okay with eigenvalues and eigenvectors?
I
As the
think we are familiar with it.
okay.
Some big thing.
You want a refresher?
Yes.
Yeah.
Okay. Yeah.
So basically, if these eigenvector are the direction of this eigenvector for the covariance matrix is the direction of the spread of the data, and eigenvalue is the magnitude of the spreading.
Okay.
So basically, if you have a randomly spread of data,
The sentence which you mentioned, you've written it in the document.
I'm sorry?
The sentence which
Yep.
you said you.
Nantachai,
Yep.
do you want a pen?
No, it's fine. It's fine. You have everything.
Alrighty.
Okay.
It's specifications.
So if we have a spread of data like that, eigenvector and eigenvalues tell you the direction and the magnitude of the spreading. If you have two dimensions, so there'll be the principal and the secondary vector and eigenvalues. So the magnitude of this is determined by the principal eigenvalue, and the magnitude of this is determined by another eigenvalue, and the direction are determined by eigenvectors.
So this means that eigenvectors of a matrix are always perpendicular to each other.
They're not perpendicular, sorry.
They're not.
Yeah.
The spread could be.
It can be three-dimensional, like,
It could be three-dimensional if you have three-dimensional data.
But for a covariance matrix, if you take a covariance matrix, it tries to fit a orthogonal.
It is orthogonal, yeah, but I don't think it's perpendicular, right?
Orthogonal, yeah, it's perpendicular. Yeah.
But in reality, it's not really
Yeah, but
always perpendicular.
for a matrix, eigenvalues, eigenvectors are orthogonal. That's how it identifies.
Okay. Okay.
So
you
in a
have
general
solution
matrix,
to your function.
in a general matrix, the
Vectors are
eigenvector, there are two eigenvectors. So just if you have time to plot it.
Yeah, I'll plot
But,
it.
yeah.
Yeah. But this one, I just want to show how to derive eigenvalues and eigenvectors.
So the Nantachai's first equation, so AB plus lambda B, is because any vector lying on the eigen. Okay, so can I explain
Yep.
a little
You can.
fundamental thing about? So let's say let's take some example. Okay. So there is a vector like this, right? So let's say 1, 1. Okay, 1, 1 vector. So you multiply this vector 1, 1. Give me any matrix. Just say some matrix.
2, 2, 3, 1.
2, 1.
minus 12.
Minus 1, let's say
Minus 3.
2, right? I don't know.
Okay.
So can you give me the result? So it is 2, this will be 3, and then this will be 1, okay? Okay, so when I multiply this matrix by that vector, I get that vector.
yes.
So if I plot that, so it will be 1, and then somewhere there 3, right? Okay. So then that is my resulting. So what happened as a result of multiplying this vector by a matrix, a vector got rotated and scaled. It can scale up or down, right? So it got rotated to left and then it scaled up. Now let's look at the eigenvalues and eigenvectors of this matrix. Can you put okay, just put Ike.
Yeah.
Can you get me the eigenvectors and eigenvalues?
This one?
Yeah, 2, 1, minus 1, 2.
I think if you command like brackets some two parameters equals the I, it will give you the eigenvectors and eigenvalues.
Yeah, so if
If you put brackets before I.
yeah, so if you put I and then put
two
E,
yeah,
EV.
exactly.
EV.
So it's like
Okay.
EV equals I.
Okay. I see.
Yes. So
Those two on the top are the eigenvalues.
Apparently they are imaginary
it's fine. So we have imaginary numbers. Fine, because we have 2, 2 here, right? So let's do a little different. This will have real numbers.
Okay.
Right? So 2, 1 means like this is 3 and
Yeah,
this
it's
is
2
0,
imaginary.
right? So it is like it will be rotated to that. Okay.
Okay, if this is one, then it's not imaginary.
This is 1, 1.
Yep. Because if you have minus here, there'll be a.
Yeah. So 3, and then this is 2, right?
Yep.
So then it is 2, 3 is somewhere there, right?
Yep.
Okay. 3, 2. And then the eigenvectors. What are the eigenvectors? One is 0.5 minus 0.85, right?
Yes.
So can we multiply this whole thing by something like 5? Can you multiply e times 5?
E times 5.
Yeah.
Okay.
2.6, right? So 2.6 and minus 4.2, right? So then one eigenvector is somewhere in this direction, right? Okay. And the other eigenvector is here, right? Minus 4 and then some pointing at that direction, right? Or something, I don't know, that direction, right?
So
No, both of them are negative. I think X and Y both are negative. Right?
So 2 minus 4 is pointing there.
other one is pointing.
Yeah.
Otherwise, other one is,
Pointing there.
oh, there. Oh, right, there, right?
Yeah, but this is just direction. This is not the magnitude.
Yeah.
So this is the direction of the one eigenvector and the other eigenvector, right? So that's the direction. So you see, this eigenvector has a bigger eigenvalue, right? 2.6. Oops. 2.6 positive.
Yeah.
And then the other eigenvector has 0.38, which is smaller, right? But our resultant vector rotated not to that side, along to that eigenvector, right? So meaning eigenvectors are attracting the first vector to their sides, right? And then the attraction power is proportional to the eigenvalue. All right? Is that right? So like if I go back and then say take a cartoon example, if there are two eigenvectors like that and that, right, of a matrix, and then its eigenvalues are 2 and 1, right, and then there's a vector like that which way will this vector be rotated if I multiply it by that matrix that corresponds to. It will be attracted to that, and then it will be scaled up or down. It will be elongated, right? If my eigenvalues were like 0.2 and 0.1, what will happen? So it will be rotated this way, but will it be scaled up or down?
Scale down.
It will be scaled down by 0.2. Okay, so it will be shorter, but rotated this way. Okay, so now coming back to that equation, why AV equals lambda V is if on your eigenvectors, right? If there's a vector right along your eigenvector,
Always scale.
it won't be rotated because other vector is perpendicular to that vector, and its rotation power is 0. Right? It cannot rotate because the torque is 0. Yeah. Is that right? By the principle, because the eigenvectors are orthogonal, and then any vector along the eigenvectors, if these are eigenvectors, I can write just as a lambda v, which is a diagonal, right? Lambda 1, lambda 2. Okay, is equal to that. So it is as if like I'm multiplying by a diagonal eigenvalue vector, because this value is just multiplying by that eigenvalue only, and then that eigenvalue only, and then they all be in rotation. So as far as V are eigenvectors. For anything else, that equation is not true, and then they get rotated and scaled. That's the whole point. So the covariance matrix is having eigenvectors along that and that to show that if you multiply any vector in this space by that covariance matrix, everything will tend to rotate to that side, not to that side. Right? Okay.
There's an interesting web page and research here about that. That's one of the interpretations. For example, it says, okay, if it's about a rigid body, the eigenvector is the natural axis, and the eigenvalue is the inertia around those axes.
Yeah.
So it gives you the natural axis if you have that scale, the distribution of the material. And for a control system, the same as rotation. Eigenvectors are the basically the input-output orthogonal space.
Yeah, I mean, it can be extended to any, let's say,
Yeah,
for example,
exactly.
there's a rubber sheet, right?
Yeah.
There's a rubber sheet, and then this has more stiffness along this axis, and then it is easier to stretch that way, difficult to stretch that way.
Yeah.
Okay? So then it has a stiffness matrix. Okay? So it has a stiffness matrix, some K main, right?
It
And
actually
K
gives-
minor, K minor, and then we know that F equals Kx, right? Stretch as a vector, and then force. So, and then let's say if I have X as K inverse F, right? And then depending on the eigenvectors of K inverse, if I pull it this way, right? If I have a dot here, right? If I have some dots here, a circle of dots, and then if I pull it, and I'll see these things elongating that way. Okay. So basically,
Actually, it has an example for that, kicking a ball,
yeah.
and it actually become flat in the direction of less stiffness.
Less stiffness.
Direction.
So I think this would be a easier thing to remember.
Yeah.
If you take a rubber sheet and then you try to pull it, and then if you put some circular dots, and then you will see the dots going in that direction. So basically, it will be in the less stiffness direction. It will be elongated. No matter which way you are going to pull it, right? So that's the whole point, right? It attracts to that thing. It's an attractor. So For the covariance matrix, it says there's a tractor that way for the data, right? It's most variable in that direction. So then, in other words, we call it the principal components of data.
Now that
Right.
you're standing up, and ask another question.
So,
So in a linear dynamical system where we
Yeah.
have x dot equals ax
yeah,
plus bu.
yeah.
So what's the interpretation of the eigenvectors and eigenvalues of the system?
So in a dynamic system, so let's say take a discrete dynamic system. Right? Xk is xk plus 1 equals axk plus buk, right? Okay. And then you have a control law saying uk equals minus k xk, right?
Okay. State feedback.
State feedback. And then you substitute that there, and then you get a minus bk xk, right?
Yeah.
If your eigenvalues of this matrix are less than 1 within the unit circle, right, which is less than 1, what happens is, no matter where your state vector is, xk plus 1 will be less than that, but rotated in some direction, right? Then xk plus 1. And then xk plus 2 will be rotating in the same direction depending on the eigenvectors of that, but eigenvalues are less than 1, right? And then it will be rotated. So then what will happen is this will go round and round and converge.
Stability.
Alright? Stability. If it is a continuous dynamic system, if it is x dot equals ax plus bu, same thing, u equals minus k x, then it becomes x dot equals a minus bkx, right? So that means, like, if you have a state vector x, your next velocity of that state will be, if the eigenvalues are negative, right? Negative means the projection will be in the opposite direction, right? So your x dot will be in the opposite direction always with the rotation. So because then the next state is your previous state plus sampling times into x dot integration, right? So your next state will be less than that, right? So the point is, for a discrete dynamic system, the eigenvalue should be less than 1. In a continuous dynamic system, eigenvalues should be negative, no matter what the eigenvectors are. As far as they are negative, the velocity will be in the opposite direction, the speed of x dot, right? And then this will converge again in the same way. All right? So these things usually are not in the books.
No.
That's
So
it.
the discrete system should be
Less than 1 within the unit circle.
less than
Yeah.
the same as the continuous system.
In the continuous system, it should be negative
Negative, yeah.
because it's the speed, right?
So yeah, that's something.
So I guess I don't have to do anything.
Is that right?
Good.
Yeah,
It's a good tip.
Yeah, good.
You do want me to go through how to mathematically compute eigenvalues? No? Should be okay, right?
I think it's fine.
Yeah. So get back to what Thrish said. I'll just do the plotting in MATLAB. How can we, from the covariance matrix that we found earlier, this matrix, how could we plot them? Plot the eigenvectors and eigenvalues. So I have a code here. It's quite long. Just run. use with eigenvectors for this.
Yeah, so it looks not orthogonal because your scale is different, right?
Okay.
So if you put like minus 1.5 to axis the same.
If you type axis equal, I guess it.
Okay.
Now if you say the axis rate,
Looks a bit small. Yeah. So the pink one is the principal eigenvector, and the green one is the another eigenvector. So what if what
it looks
would
perpendicular, right? So
Hmm.
it is perpendicular.
I think if you do a cross product, it's a result.
Yeah, you can check it. You can
cross
check
product.
the cross or just inner product of the two eigenvectors. It will be 0.
how can you do that?
Yeah, dot.
Dot.
No,
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 dot.
DOT. S or 1 or 2. Hasita, do you know what dot product is? What do we mean by the dot product? It's the projection. It's the projection of it's almost 0, right? So it's okay.
No, but
So
dot
it is
product
the
the
projection of
Yes.
one vector
Yes.
to the
eigenvalues. Oh, yeah.
Eigenvector.
Yeah.
Okay. So it's 0, which means that they're perpendicular.
They are orthogonal.
Yeah. Okay.
So it is
I'll-
what do I mean by projection is like the shadow, right? So it's like if you have two vectors. If you have V1 and V2, the dot product, right? The dot product is this thing. That's the projection of one vector on the other. Sorry, this projection. So if they are orthogonal, the projection is 0, right? Shadow is 0. That's what we mean by that.
Okay.
See, this little thing has a lot of fundamentals that we use throughout, control systems, and a lot of people don't understand this.
Yeah.
Like what Trish said, what if we have a new data point coming in? Like let's say we said our new V is some random point. Like let's say this one is minus 0.1 and 0.1. We plot them.
So this is another data reading?
Yep. A new vector, really.
A new point.
Yep. Right. So this new point, so let's say I have a new vector here. What is eigenvector, eigeninformation is good for is that it can be used to predict the evolvement of the system, like what Trish has told you about this. So we could use this to see how in the next cycle what the system would behave. So in this case, I had a program run for like let's say 5 cycles. Let's see what would happen. So let's move on. In this case, I say that my first point is here. So after 5 cycles, since the eigenvalue is so small, less than 1, I guess. Eigenvalue is so small. That's why it starts to turn to the principal eigenvector and then go to 0. Okay. So
Because every time it multiplies by less than one number, it gets reduced to 0, right? It converges towards 0.
I understand this. I don't understand where the time parameter came in, because you had your data readings. and
like
you were
let's say
done.
we have a discrete thing. We have
That's a
first.
discrete version, because
Yep.
of multiplication.
So basically, it is nothing but this one is our eigen. It's covariance matrix S, right?
Yes.
If we have another new V at time t,
Another V means another reading between X and Y.
Yep.
Right?
so we can get Vt plus 1 by multiplying this.
Vt times the eigenvector.
Yep. No, not eigenvector, the covariance matrix.
Ah,
So what does that mean?
Yeah.
Why you?
So now he's taking covariance matrix as just a matrix.
Yeah.
Okay.
So it is multiplying one data point,
By the covariance.
and then say how
Oh,
that
okay.
data point will be
Yeah.
propagated. If you keep
Similar to this
multiplying.
one.
Yeah.
What it shows?
Then it attracts to that major eigenvector and then keeps going to 0, just like.
So this one, because the
What is the meaning?
Oh, the meaning is like, so if you keep generating data, so from that system,
mm,
you will get data, getting all this kind of attracting data
Okay.
towards that direction.
The trajectories and control systems, when you have the trajectories
Be-
moving towards.
yeah, because the covariance matrix tells you about how the system behaves
Yeah, so
initially.
like if I asked this in one of the exams. So it's a practical implementation of that is let's say somebody is operating a lung, right? Right. So now the lung expands and contracts and expands, right? So let's say now you're operating, like when you look at the operating site through a camera, so it's like a vector, okay? So now what happens is when the thing expands and contracts under the camera, my operating point like moves that way and out of the field and comes that way, right? Ideally, if I can have the camera along the major eigenvector, this point will be coming up and down along the camera, right? So then how do I find that axis? Like I take this data and then real time I calculate the covariance matrix and then find the eigenvectors and eigenvalues, and then if I find the eigenvector has the highest eigenvalue, I orient the camera towards that, right? In the laparoscopic camera, and then I see suddenly now my sight is coming up and down along that axis most of the time.
Yeah.
Okay, so that is what it is. That is really, really useful in dynamic systems if you know what that really means.
Yeah.
Because it's really a
In the
tractor.
experimental point of view, because
Yeah.
we draw these attractors in control theory,
Yeah,
but
yeah.
that's the deterministic things that that's on paper.
Yeah, it's like the phase plot, right?
Yes, yes.
But why the phase plot goes that way is because of this attraction.
So basically now, I mean, we have a system
Yeah,
which is determined by the covariance matrix.
yeah.
Yeah.
So this is now like the system matrix of
Exactly.
a dynamic
Dynamic system.
which the data which
Yeah, so it tries to get this, if you look at a phase plot, it comes and then goes along axis, right? All the time, if it is a stable thing. So then, so basically, if given a data set, you can see the tractor properties of that underlying dynamic system using this. So it always tries to track things in that direction.
But that would be for chosen region or chosen point.
Yeah. So,
no, just example.
No, just for
dynamic
Yeah,
system.
Yeah.
Okay.
If you have questions asked now, like we can go into really, we have to really go to the real bottom of this. Those people who know this will really do it differently.
Yes.
And you see the world differently now.
Exactly.
Right, so
I'll give you the code of this. You can generate it.
I want to add it to my notes.
When Holly is taking a picture, and everyone else has to take a picture.
Okay, question. Did you pass a statistics course in America? The thing is,
Mechanical engineers don't.
yeah.
I don't see this in any book or any lecture. So this is original.
Well,
I mean, it has to be an insight. Really, people don't. I mean, people study this in a very dry manner. Like,
Because
oh yeah, this is a matrix. Get the eigenvectors. Oh yeah, what is that?
Because I remember when
That's how I was taught. I mean,
Yeah.
this is what, like 10 years ago, we did all this linear algebra, right? And nobody really explained the whys or hows,
Why
why
that,
it
right?
relates.
Why is that?
But which courses did you do? Because it also depends on me when you're not. Because me coming from a mathematical background, I didn't see the application size of what you guys are saying, but I saw all the rigorous derivations of them.
Sure. So we were taught. Okay.
Sorry?
I did linear algebra. I did maths 1,
That is
2,
not the way
3,
to do it.
statistics.
This is
It's a
the
new
initial
vector.
New
vector.
electronic engineering.
Sorry?
Just
For
random
an
point.
engineering
For
point.
engineering.
The thing is,
Vector is
its
purple,
mathematics came from
No,
the
this is
experiments.
eigenvector.
So the thing is, I think in
This is the
universities,
evolvement
even
of the system.
in pure mathematical
BT,
courses, they
we have
insist on the
BT plus
real
1,
application and
it
experiment
attracts
based
to this.
application
Sure,
are so on.
but
And so
for
on
me,
and so on.
I did this as a prerequisite to a quantum mechanic course, so the
And so
application
similar
for
to
me
this one.
was in the electronic shells.
Mm.
So the behavior was
This one
different,
is
so I have
BT,
seen an application, but
BT
in a
plus
different
1.
format that you guys are using, and the scale in which that I saw it was different. So for example, what we have in quantum mechanics, electrons are point particles.
Okay.
This
So
one.
what you see here, we
He's
don't have
just
selecting a
multiplying
certain region.
it
For
again
example,
and
what
again. So he's
Thrish was
multiplying
doing
it
with
once.
The
examples.
density, right?
Why he gets
You can track the
matrix,
density,
then he gets a result.
something like that.
He's multiplying the result
No, because we
again.
have a probabilistic point of view.
So
we
what's
give
happening is
probability
that this
density, we don't
covariance
have
matrix
density
is
for
now
electrons.
acting like a dynamic.
Even the probabilistic
When you
point of view,
throw
you
a
have a
point
dynamic
at it,
system.
Yeah.
Okay.
Just to
what's
And
gonna
that
happen?
dynamic system,
So when you
any
multiply
dynamic
one,
Point is a
system
vector.
attracts certain
Point is a
eigenvector
vector.
and has a
And then
phase,
the
basically,
covariance
a phase
matrix
diagram.
maps
Showing
into
that.
another
So that's
vector,
basically the
which
phase
is
diagram coming
which is
out of
in its
experiments.
own
I did it for mechanical system.
major eigenvector
probability
direction.
system.
So that's what it is.
We should be able in fundamental to relate these, but I didn't know about covariance having the same role in the dynamic system as I had.
Yeah, it says everything integrates, like come to the same same base. Like if you look at it as eigenvectors, basically as attractors, right? And the attraction power
What he's
is its
saying-
eigenvalue. That's it,
No, what he's saying over here
right?
is that
Yeah.
And then
if I
it's a dynamic
multiply
system, right?
the
Yeah, attractor is a dynamic system.
by the covariance matrix, it could change the position. So this is, let's say, time.
That's all.
If we multiply the result again,
I guess
this is time.
it's
It's a-
It's not a fundamental.
Right. They're just a multiplication.
That's why it's going on.
That's what's going towards the.
Well,
the
it,
center.
it depends on the eigenvalue.
It depends.
For us, they just show.
This one is going
This is
down.
what the eigenvector is.
But it could be the
It shows
case
you
that
what the
it's going up,
calculated
depend on the
eigenvector.
size
Then
of
they asked you,
the
there's
eigen
the
information.
matrix calculate eigenvector. And nobody in between told us this is how it's used or what the application is or anything like that. Whereas if they did that, then it would have made the exam a lot easier because I would have
Oh,
understood.
no, it could go to infinity.
I think most of those guys don't even themselves have elaborated about the meaning.
I mean, this is used in learning theory. Like for example, like once depending on how the neurons in the brain are distributed, if there is some kind of a major axis for that distribution in a space, you cannot learn. Whatever your experiences are always attracted to what you know already, and then you interpret it that way, right? So it works like that. So you try to project everything to that axis. So it is known, right? In psychology, in motor learning, so many things. It's a bizarre thing, but that is how things are organized. Because everything tries to find the patterns out of the data, and then what they do is like to find the principal components, right?
Yeah.
And another cool thing about these principal components is once you know the major eigenvectors, you can forget about the minor eigenvectors and collapse the state space to a less number, right? So if it is like let's say like your data is like you have a two-dimensional thing, right? Your measurements are two-dimensional, but your data is just around here, right? What's the point of having a two-dimensional thing, right? So you can just have a matrix that rotates this thing, right? By that, and then now your x dash is that and y dash is that. Forget about y dash, right? So now it is a hyperline, right? Hyperplane. So it's a lower dimensional thing. So we use this to reduce dimensionality in data. If they are not distributed enough in one axis, just drop it, right?
If
So,
I ask something about
see,
that,
the singular value of decomposition is doing that. Okay, so we'll talk about that at some point.
one
I mean,
question.
again, I've heard SVD. I mean, I've even
No,
read the
no,
last
it's another beautiful story.
Yeah.
It's amazing and beautiful. So how what it does. Okay.
Sarah had another question.
Yes, I had another.
Well, I am not sure, but I think there is a kind of problem with this reduction of dimensions because, for example, in my experiments,
Maybe you
if
have
I-
time.
Hmm?
You have time.
No, I mean that, for example, if I change the stiffness of the joints, the variation is going to be very small. So it means that I'm going to have eigenvalues very low.
Yeah.
So it means that if I decrease the dimension, maybe I'm going to lose that information that I'm looking.
No, it is like it is saying under that condition, your whole axis, you're looking at your data in some axis system, which is complicating the picture for you, right? So you could rotate your way of looking at it, and then simplify the whole thing. So that is what it is saying. And then under another parameter set is another thing. So you cannot say this is my axis system, right? So for all what you can say is with your there you have a meta parameter which is your stiffness that rotates that eigenvector. Okay, so that's another story. So then that means the principal components is a function of a meta parameter you have control over. So meaning your whole dynamics of attraction can be controlled using a stiffness. That's a morphological computation, right? It's a morphology is doing that computation, and then you have control over that computation through a bodily parameter which is stiffness. And you have to present it that way. So that's
So basically,
problem is most of the time you don't have control, but it does what it wants.
Yeah. So then it can be a probabilistic relationship, conditional probability or something. Right. That's nice. That's nice to see. I mean, the body or the bodily computation might be using that kind of simple attractors because you don't have to control anything, right? It is an attractor, and then it kind of like wanders around and comes to home at one point, right? So then it's okay with that. Okay, that's great.
Okay.
I think those who missed this lecture really missed.
Need a lot of things.
So can we have slacks for the next
Sorry?
We should get stats.
because it goes to 3 hours?
Yeah, we should order pizza or something.
Yeah.
Shall we order now?
Well, the group is wealthy now, yeah, why not? So.
Yeah, we'll do that. So I think it's okay to do that.
Yeah, we'll have some coffee and some cookies.
For
We'll
sure.
do that.
It keeps the engine running.
I
So
think
it's not a
also
big expense. So.
this collapsing thing, I think, I might be wrong, but so in control theory, when you have your system matrix, then you convert it into controllability canonical form.
Yeah.
Maybe this is somehow related to.
Exactly.
Yeah.
It is. It is related to
Yeah,
that.
so you see, PID design is basically designing the eigenvectors and eigenvalues. You put it in your desired direction, and the gain is basically the eigenvalues. How fast they go to that desired direction.
I think we also should have a lecture on control.
Yeah, I looked at it that way. I never looked at PID control that way, but you're right, so now that you,
Yeah,
Yeah.
it's like, it's basically like
Yeah.
the eigenvalues.
yeah, that makes sense.
Okay.
Cool.
So, in the next topic is the information theory, really. So, what is information? Like, if you observe something, then what is information? So
Information
basically,
is, if you have information, there's a point, there's a reason to sample a new data point. If you don't have information, then there's no reason to sample a new data point.
If you have information, there is no reason to sample a new data because you have the information.
No. So sorry. If each data point carries information, then there's a reason to get that, right? And then if each new data point does not carry any new information,
Yeah.
then there's no point. Right?
How to know that?
So, yeah, Shannon entropy is quantifying that.
so before going to Shannon entropy, I want to just talk about information a little bit. Like, let's say if you observe the value, some y value from x. So like, let's say if the probability of x being y is approaching to 1. So this means that in the next observation, it is not so surprised if we're going to see x equal to y, right?
Yeah.
So this one is not very interesting, I would say.
Because you know for sure
Yeah.
you will get x equals next time, even if you sample.
However, if the probability of x equal to y is so low, approaching 0, it means that maybe in the next observation we get new information. Or it becomes really interesting, right?
So what is the definition of probability?
I'm sorry?
What is the definition of probability? How we calculate it?
No, it's just
general.
example.
It's
yeah,
general.
So x is the data that you're reading,
Yep.
and you
X
want
could
it-
be anything, like for example, X could be from A to Z.
Okay.
If
So X is a random variable,
And Y is
and
the
then Y
determinant.
is a X,
Like particular values.
some quantum or
Yeah.
some particular bin or something, or value. So X is, let's say, temperature. The temperature goes up and down in a furnace. And then if the temperature has settled to some value in the furnace, there's no point in going and checking it again, right?
Yes.
Yeah. And then if the furnace is all over the place, like going up and down all over the place, and then you really don't know, right? And then it might be worth checking. But even if you check it, you get just another random number somewhere,
Yeah.
right?
Yeah.
So the best way to represent this relationship is to use the logarithm of 1 equal to probability of something. In this case, x equal to 1. So which is essentially negative of log p.
Yeah, it's okay for the probability to go that bracket, but the conversion is 1. Because probability don't go negative, it's fine. So log is undefined for negative values. So put the mod side. Yeah, great.
So what does the log show?
So the log shows the information.
That's the,
Yep.
okay.
So if we plot this, let's say
Only because one's not so interesting and closer to zero.
Yeah.
Okay, I see. So they can just,
so if we have a
the value in the information is the log. Got it.
I is minus log p.
Is that right?
I'm just wondering, how do you obtain P there? Or randomly generated from 0, 1 to 1?
It can be a range from 0 to 1.
Yeah.
C equals 1.
Yeah.
That's the probability that we know that it will tend to y.
Yeah, exactly.
And then the other one, the probability that it will tend to y, but it doesn't.
Yeah.
That is interesting.
No, what he says is this. Let's say you have with time. Let's say there's a temperature.
Yeah.
Okay. So furnace temperature T, capital T, and then it is a random variable. We call it a random variable because its value changes all the time.
Okay.
And then it goes up. Let's say at some point it settles down.
Yeah.
Right? And then if we bin this temperature axis to these bins, right? So, let's say I want this bin, that is my y, right?
Yeah.
Okay. So, and then probability of t being equal to y is what he said here. Right?
Very high.
So here it is probability of 1, right? It is probability of 1, it will be in this bin.
Yeah.
Okay. So then is there any meaning in me going and checking the temperature? Right? No, right? So there's no information in new data. Okay? It is already known.
But how do you obtain that value? Because, for example, I am measuring the temperature and I am, for example, in the first peak. And I still don't know about the other
Exactly,
peaks.
yeah, we don't know, right?
So how
So-
do I calculate the cost?
Yeah, so like if the now the probability changes, right? So now what happens is now probability is assigned to these things. You keep a track of all the probabilities assigned to these things, right? And then so let's say now with probability 1 it is here, okay? And then when you have more data, you have to divide everything by the number of data, and then that probability goes now down, right? And then there are some assigned probabilities to these bins too. Right now we have probabilities for 3 bins, and then others are 0. And then when you have more evidence, and then it gathers, right? Changes all the time. And then after some point, those probabilities die down, and then this probability increases to 1. Okay? So now you have to see it as a vector now moving, right? So vector values started from 1, 0, 0, 0, and then when you have more data, others get populated, and then those probabilities come up, right? It's like now probability is, Nantachai's probability notion is P1 to Pi to Pn, right? So it's a vector now you have to look at. Okay. So now he will talk about it, and then the total sum over all the bins I equals 1 to n is the information. Okay. So the total sum
It's the entropy.
is the entropy.
The second probability, how would you illustrate it from the graph, or is just that we just diverge to, we get 0?
What's that?
How to calculate?
Oh, so 0 meaning like it's almost 0 means this data is like that. So it's all over the place, and then when you add up, these are tiny, small numbers.
Okay.
How do we get that graph if it is spread all over?
No, it's just random noise, just white noise.
So is
Right.
that really the?
So I'm listening to a microphone, let's say, right? That microphone gives me white noise, right? And then if my bins are frequency bins, and then I have all frequencies all the time, right? And then at any given point, the new point can be any frequency. So then the probability is 0 of any point.
For
Is
the way I was taught this, we were taught information and this Statistical in communication theory,
Mm.
and it was to do with compression of data.
Yeah.
So you don't need, in these cases, you can eliminate all the stuff that's closest to 1 because you know what it is, and then your data packet gets smaller, even less to transmit. So I don't know if that makes any sense. Because here you want to kind of ignore everything where your probability is in that 1. And you
1
wanna-
or even 0.
or yeah, and then you want to, well, from the communications point of perspective, you didn't have to send anything that was a 1. You could send all
Right,
anything where the
exactly.
probabilities are less than 1.
Between 1 and 0.
Yeah, and that way you can compress the data. So no matter how the data was generated, you can calculate the probability because you know the actual data, you know the history. And then for the transmission part, you only transmitted the deltas or the changes or where you had actual real information.
Yeah.
So it doesn't matter how you get the data and how the probability is calculated. Every system will be different to be able to calculate those probabilities differently. But once you have it, you've got all the information, and then further processing down the line will rely on whether it's actually regarded as information or not.
In your case, how do you calculate the probability in your experiment?
In my experiment,
Yes.
I just fit the probability distribution.
You can fit a PDF.
Yeah.
Ah.
Like let's say you have 50 trials of data, right?
Okay.
And you fit the probability distribution of those data.
Ah.
Okay. So basically, without the sum is just the information.
What do you mean by fitting probability distribution?
So like
I don't understand.
And binning?
That's the bin, right?
It's just collecting data between a range, like from 0 to 10. The values from 0 to 10, how many data you collected, you record it.
So it's
And then
just
from
like-
10 to 20, all your readings, that's your bin. And then from 20 to 30, you fit all the data in that range. Or you
So
can use
bin
range,
comes
0
from
to 5,
the
5 to
same
6.
original bin idea, right? Let's say I'm throwing a ball, right? I'm throwing a ball, and then I don't know where it is going to land, right? So it's a random, like the position of landing is now a random variable because it changes, right? Across my throws. So then let's say, like I throw 1,000 balls, right? Now it is a random variable because each ball lands in a slightly different place, right? And then if I put, now I want to know how many balls fell on one particular place versus another. Now I put some series of bins, right? Okay, so just physical bins like that, right? And then I collect the number of balls that fell on each bin. Okay?
So is that really the probability of the distribution in one parameter
Exactly.
that we're interested
Yeah,
in?
yeah.
And that's the information.
That's it. So,
Right, no,
did you get it? Right? Our bidding is nothing like, just
It's just
physical
based-
bins,
Based
right?
on collected data.
These are bins.
Yeah, because if you think it's predicted.
And then I throw
maybe
balls.
the next day it's not known.
And then
Yeah,
let's say
it's
this
predicted.
bin get 2 balls, and then this bin gets 3 balls, and then this bin got a lot of balls, and then this bin got few balls, and this 1 ball, and then the now I count the number of balls that fell in each bin, right? Temperature data falling in that bin. Okay, is the same. Now if I take a count, then I knew that I threw 1,000 balls. Then I divide everything by 1,000, and then what I get is a probability distribution. Right? This the total sum is 1, and then there's a distribution. Okay. So that's it. Think very simple. I mean, these things are coming from very simple concepts. It's not complex. Like people make it complex. Oh, from PDF. What is that? That's it.
Yes. For example, you have your probability with your 50 trials, you generate your probability distribution. So for example, I am taking another trial. So how do I know that it's going to be worth it to take this trial? So I just use the first.
Yep, you could use this. Or you could use channel distribution.
That's a lot of things, right?
Yeah.
You understand?
Yeah.
So you're not what it's worth it to.
To take the whole trial or not?
If you got, so say you got any a time value, and you know the probability of what y t is going to be, what t is going to be, based on your historical data.
the whole probability is below 1.
Then you could
All the,
try
yeah, probability is below
based
all
on
But the,
historical probability.
but what I mean is like, for example, let's say, okay, I am in the third time, for example, when t is equal to 3, and say, okay, with this gate, I can say that it's not worth it to measure all the other time because of this. No.
Yeah, I don't know. I think it's all based on collected data.
Yeah, you can't say that,
Thrish, is that
like
correct?
especially when you have the 3 points.
Am I correct in
But
saying
I'm just saying.
that
Yeah,
like
like
the information
this could be
is
a
all
trial,
based on
right?
collected data and not predicted?
What data are you collecting for?
Yeah.
historical.
So,
This could
yeah.
be false.
So Sarah, it's
So this whole landscape keeps changing, right? So like
All based
with
on
evidence.
Maybe after this round.
That is how the basic influencing comes. So you have a prior distribution, and then your posterior keeps changing with new evidence. Alright?
Yeah,
Yeah, so what you're
because
trying to-
you might
can't
need to
make
use
a
information
decision
plane.
whether to collect the data or not, or whether it'll be information flow or not. It's a post assessment, a post analysis.
Okay. So,
Just explain, so the contour would be something like that, but the general, but the actual value would not be such a small.
No.
It would be something
That's
like
why-
a blue column.
Exactly.
yep,
That's why
this
we have
is
to
a
fit
current
it.
fit.
So we fit it, and then because our binning is very discrete, right? It depends on the bin size and everything. Then after that, we need a smooth curve because we need intermediate data. So,
I mean, what I'm saying is, the actual columns are not like this, one might be.
yeah, exactly, yes.
It could be like,
Exactly.
It is very sporadic sometimes. And then still, for our practical purposes, a smooth curve is.
We
fine.
fit it, we
Yeah,
fit it.
yeah. Because it's then once we fit it, it's low dimensional, right?
When you bin it, like principally, it was the same question. So you fit the probability distribution. What value do you take? So I can easily generate a distribution.
Yeah.
But what is your probability value that you put in your Shannon entry? or you put it in edge?
All of it.
All of them. If you use channel entropy, you have to use all of them.
Okay.
Because this channel entropy or Kubrick linear divergence is not compare point to point. It's comparing the whole distribution with another distribution.
With a new point or another distribution?
Another when you make a change in your system, for example, change in the stiffness, you get another distribution of torque, right?
Yeah.
So you have to compute that distribution, compute the KL divergence between that distribution and another distribution.
Okay.
Yeah.
All right.
Okay. I'll look into that. Yeah. So the concept of information is clear. Okay. So the next one, channel entropy. So the entropy is a measurement of information. So like if we observe something repeatedly, like in this case, which case? So in this case, if we observe this repeatedly, y should follow x. So we want to find the average information obtained when we observe this repeatedly or continuously. So this is what we call channel entropy. So I'll slowly derive the formula of channel entropy so that
It is really, really important.
interesting.
It has a beautiful.
So like, let's say if we have two systems, two machine 1 and machine 2. This is going to be quite simple example. So both machines are capable of producing 4 letters. A, B, C, and D. Okay, the probability of machine 1 producing A is 0.25. For B, C, and D as well. Okay. Well, the machine 2, the probability of producing A is 0.5, B is like let's say 0.125, C is 0.125, D is 0.25. How can we know that which machine would produce more information? So more information means more surprise for you. So less predictive.
Less predictive.
Machine 1.
How can we mathematics? Yep.
Machine 2. Machine 2 has more.
Okay.
So let's let's say imagine like machine 1 is producing objects of sizes, different sizes, right? And then machine 2 of those sizes, right? Which machine is more interesting to be looking at? Like so, machine 1 is boring, right?
No.
Because
we'll see this.
Machine 2 has a half, and most of the time it's going to produce
It
A.
would surprise you, don't know which one you're going to get, but it's a likelihood of
So, like, if it is a kid looking at these two machines, the kid looking at machine 1 will be bored
I think
because it's same sizes coming out, right? And then the second machine is interesting to look at because different sizes come out.
Let's channel entropy
Machine 1 is also producing different sizes, but it's
So-
producing them on an equal
Exactly.
basis.
So then there's no point in watching it. Right?
Yeah, there's no point in watching.
Yeah, so you know 1/4 of the time it's going to be
You can leave it aside.
So in terms of information, do I get any information by staying there? I know for sure it is going to be that
This
one.
side is what, machine 1? Oh, machine 2, machine 1, right?
Two.
Yeah, I would say.
2. So channel entropy
No,
is defined.
it does know information only, so.
But surely it depends on what we are interested in, because if it's not the size that we're interested, but the pattern when A, B, C, or D are produced,
Yeah.
and how frequently. So even if the probability is 0.25, at what time intervals are they produced?
then the
Are they
random variable
one
is
after
different.
another? Yeah.
Then when the random variable is different, so it's a time random variable.
Yeah.
So here the random variable is the size.
Yeah.
Okay.
That's what Shannon said.
So basically Shannon entropy is defined by this equation. So it's the sum of the probability times the number of, well, I put it this way, the number of yes or no question required to obtain each letter. So like, for example, for machine 1, what is the number of yes or no question that you need to require to obtain A, B, C, and D? So I would say for machine 1, I'll say the first question, is it A or B? This is my first question. If yes, no. Okay. And is it A? If yes, then we get A. Otherwise we get B, right? And then is it C? If yes, we get C. If no, we get D. So what is the Shannon entropy of machine 1? So Shannon entropy of machine 1 would be to get A, you require 2 equations, right? So you get the probability of A, 0.25 2 plus, to get B, you also require 2 equations, 0.25 times 2 plus C and D as well. Which is equal to 2, right? So this is the entropy of asking one. The average equation there is required to ask the machine 1. So the
The entropy is saying that at the average number of questions you have to ask to get an answer.
Okay.
Average number of yes or no questions you have to ask.
Yeah. So here, so we asked.
For all, like you have to ask 2 questions, right? 2 yes or no questions.
Yeah. Yeah, we asked 2 yes and no. We asked 2 questions.
Then won't it be the same?
okay. How about machine 2?
Submission 2.
No, it's not.
I think the video is capturing that. It's fine.
Yeah.
Can I rock this off?
This is a very engaging tutorial.
Yeah, you
And it's good that's interactive.
What?
Can you explain that 0.25 times 2?
Okay, because it follows this Shannon entropy formula.
Okay. So the probability times the
Probability.
The number of yes or
number
no
of
questions.
yes and no questions.
To get that letter.
Mhm.
Okay.
So we say that is 0.25. To get A, you need 2 equations.
Oh, okay. For all times.
Yeah. So, but it can be different now. For machine 2,
Yep.
some are 1 question and then some are 2 questions.
Okay.
Can I grab this one?
Yeah.
But wouldn't the questions be the same?
No.
No, because they have.
You will see.
different probabilities.
So for machine 2, we want to ask yes or no questions, so it has to be 50%, right? So we ask, is it A, If the answer is yes,
So
then we get paid.
why wouldn't you ask if it's A or B?
Because we want 50-50. We want like
You only
yes
want-
and no question, yes and no answer.
Okay, so the probability of, so then,
The
why?
graph is the same.
The graph is
So
the
the
same, but the
probability has to be
probability
matched,
is
to match with the, okay, I see,
Okay.
I get it now.
If no, then we have to ask, is it D? If it is yes, then you get D. If it's no, then you have to ask another question. Is it B? If yes, you get
You should not ask is it B or C?
You could ask, is
Oh,
it
okay,
C
yeah,
or
sure,
is
it's
it
the
A?
same thing,
Yeah.
same thing, yeah. I get it.
So
Okay.
for the entropy of machine 2 would be 0.5 times one question plus 0.125 times three question, 0.125 times three question plus 0.25 times two question, right?
What is 2 and 3?
The
Number of questions.
Number of questions we have to ask.
So here's the number of questions.
Okay.
Yes or
why
no
each
question
one
we
is
could
equal
obtain
to
it.
1 to 5 is equal.
H1 is equal to 2 because we calculated from here,
Ah.
from machine 1, sorry.
So this is, what's that, 2.5?
Okay.
So you have to deal with the highest probability first.
No, you have to generate
No,
a 50-50.
that's
Yeah, this one is a very simple scenarios that has a 50-50 chance.
So the answer, because the answer can be
Okay.
changed, so the answer has, in terms of the outcome, probability should be like 50-50.
In this
In
example.
this
yes.
example.
But if you start with B, then the value there will be changed.
But you should start with B then also for A for machine 1. So if you start with all the different probability states of questions, I guess, if you're starting with machine 1 with A, then you must also start with A with machine 2.
Okay.
Then it should,
Well, the reason why I start with A because for machine 2, the A has 50% chance. I made it purposely so that it is
so,
easier
okay,
to
so then
follow.
what's the rule then for building the question? So
You could,
So
for
you-
this
you
case,
went
you
in
can
order.
start with anything.
So you went in order of probability.
No, it doesn't matter.
It doesn't, you sure? See, because you did A, then D, then B, right?
This one I could also ask, is it B or C or D? When it's no, then it's A. Right?
So your first question.
But what if you ask if the question is it B?
But that's the wrong question.
Yeah.
That's what I'm asking, how would you define what the rule is
Because
to ask the
we,
question?
you want only yes or no question. So then the chance would be only 50%. Right? It could be either yes or no.
Yeah, if you ask is it B?
So let's
then
start
it'd be
with
yes
B
or
then.
no.
Is it B?
Then is it B? Then no. You can't do that. Yeah.
Why? I don't understand.
Because
No, no, no.
B has a probability of 0.125%. So when he says is it B, you don't have a 50% chance of having yes and a 50%
Okay, so
chance
the
of
rule
having no.
must be,
Exactly.
the things that you're asking the questions of must be matched probabilities.
Yeah.
Okay.
And that way you ask
Yeah, is
the
it
best
A?
questions.
Yes.
Alright. So then you always
No.
tailor questions have equal probability.
In this case, yes.
It
Yeah,
is.
just so that we can show the number of questions. to do.
Okay.
But there's a way to calculate the number of questions.
Okay.
So the H2 would be variables. 0.5 plus 0.75.
1.5.
2.5.
Right?
Yeah.
No, isn't it 1.5?
We need another
Oh, 0.75,
0.75.
yeah.
We need another 0.75. Because you had two.
No, this one is when they combine the 0.25 times 3 is 0.75.
Okay.
Yeah.
Okay. 0.25.
It's easier to go that way.
Yeah.
Yeah.
Slower.
So H2, so H1 we have to H2 we have only 1.75.
That team.
Yeah. So
Yeah.
so machine 1 has higher entropy in this case.
So what does that mean?
I read the answer, but wrong correct answer.
So how can we?
So
This one is like, well, we have to keep tracking number of questions. And how can we mathematically compute the number of questions required?
But if we change the order, then the answer will be changed. Isn't it?
What order?
Let's for H2.
So like n minus 1.
If we take B into the front, then A to somewhere in the middle, then
But in machine 1 it doesn't change, right?
Yeah, for this
Then
one,
machine
as
one
we
will be
said
the
that
same
we need
because it's the same value.
50-50 answer.
The thing is, you're trying to ask the least amount of questions. So
Yeah.
if you ask,
Minimum
is
number
it
of
A?
questions.
Is it A? That's a 50% chance it could be yes. And then 50% it could be no. And then when you say, is it D? That means there's a 50% chance that it can be D.
So basically this branch is it D, right? Is it D, yes is 0.25. And then no
It's also
0.25. Because you add these things together it is 0.2. So always this is symmetric.
Your answers, 2 and 1.75, what does that mean for each machine?
So it means that machine 1 has higher entropy, so higher information.
More information. Okay.
So
Yeah, okay.
So in the next observation there'll be more surprise. Machine 1, think about it that way. Yeah.
Now by more information again.
Yes.
It means more variation.
Exactly. So the higher the uncertainty,
Okay, high.
the
So, but
higher.
it is not a linear. Higher the uncertainty is not really true, right?
Hmm.
So if it goes to white noise, then again it drops.
Would white noise be maximum?
Complete surprise is also no information.
Can I drop this?
Can somebody taking a picture of that?
Everywhere.
Oh, okay.
yeah, even straight forwarding.
So what it says is like, okay, so that goes on, information gathers, and then beyond some point it starts to drop.
I'm not sure if I understand this because if the probabilities are the same for each case, they're not changing, then what more information can we have because we already have all the information that we need?
Yeah, so no, I thought that way too. So, but what Nantachai's example is saying is, it depends on the exact probability too, right? It is not like very small probabilities and then a lot of possibilities. It's just four possibilities
I look at
and
this.
then like quarter possibility.
I got an analogy. So you're making a fruit salad, right? You're mixing fruit salad. And in machine 1, you've got apples, pears, bananas, and grapes. And it gives you
No one has the surprises.
well, it gives you more of every. He gives you a fruit salad because it's an equal distribution of all the different fruits. Machine 2 is giving you more apples than anything. Might as well call it an apple salad. So it's not giving you more information; it's giving you more of one thing.
Yeah,
Yeah.
something like
Nice.
that's a good one. That's a good. That's a good.
Yeah,
one.
that's good explanation.
That's a good explanation. Yeah.
So the Shannon entropy is defined. How can we know the number of questions required to yes or no question required to obtain each letter? How can we define this? And it's somewhat related to the
N
probability.
minus. Oh,
You said it's what?
oh no, I was going to say n minus 1 because you have 3 questions.
more, but
Was it by the ratio of the probability?
Okay.
Say the logarithm.
So some kind of ratio of the probability.
I think it's a logarithm of
Okay.
I think
Because
that-
that's- Where does it
The
say?
logarithm.
So it's,
Or because you don't know that.
NI is essentially
Oh,
this case. So if we try to prove it, so log
Yeah, base to the base two. So because you have yes or no questions,
Yep.
right?
0.25. So would the answer be 2? Should expect to get 2. So let's say log 2. 25. Yeah, the answer is 2. So what if we have this? The answer is 3. So Shannon entropy is nothing but, and this one we can represent it in a way that other people.
But that is cool.
So it equal to,
Number of yes or no questions on the branch.
Yeah.
so this is Shannon entropy, and the order of the logarithm depends on the nature of
And
the
minus negative, what happens then?
Oh, right, thank you.
Nice.
Very cool. So, this good. What if, can I wrap this off now?
so PIs over here would be this one is, so this is, and in this example, what are the PIs?
0.25.
0.25.
Uh,
So we want to determine the number of questions required
And
to
over here,
ask.
so they're changing, right?
Yep.
0.5 and-
Yep.
So that's, there's the summation somewhere,
No, this one is just to calculate the number of questions required. So in this formula, it's gonna
right?
result.
For each,
So some them are.
for each one. So you have H for A, H for B, H for.
No, no, no.
And-
No, it is a sum for A, B,
Ah,
C.
okay.
So
But
like,
we have N for A.
Yeah, yeah,
Right?
So one question, in the first machine, the n is basically 2, so that means that we should take how many samples, 8?
there are two questions on average to get to that answer.
Okay, 2 questions together.
Yeah, so the total entropy is saying, on average, how many questions do you have to ask? How many yes/no questions do you have to ask to get the answer?
That is 2.
So if you have more questions, that means like, yeah, so that means like yes, so you have to wait more to get the answer.
For the other one, it is got 1.5, which is less. So it means.
Meaning you get the answer quickly on average.
So thinking of
So you know
the
like
fruit
for
salad
the-
that you talked about. I
know
know one
people have
example.
to vary the stiffness longer or shorter. You know,
So,
they do
like,
it
let's
quickly,
say, if we have a
calculate
fruit
to the
salad
point or not.
comprised of like 2 different fruit, apple and banana. In that fruit salad, let's say I have 2 possibilities, right? It's either apple or banana. Let's say in first observation, I said I have only apple. So the probability of getting apple is 1. So the probability of getting banana is 0. And the next one, Next observation. Probability of getting banana increase and this decrease. So they have to sum up to 1. So it keeps going. If I have this, I want to know when do I have higher entropy. So I want to plot them really. So basically, P of A is, no, P of B is nothing but 1 minus P of A, right?
Okay.
Okay. So can I call, I'll call this Q, and P of A, I call it P. So let's plot this. So what I do is I plot from P from 0 to 1, and Q is the from 1 to 0 basically. And I compute the Shannon entropy given these two distributions, so I sum them up. So now Shannon entropy is, sorry. Is what is negative P log P minus 1 minus P log right? Okay. So basically H is nothing but minus P log 2 P plus minus Q log 2Q. Okay?
The sum of the two.
Yes,
So basically this.
Okay, adding them together.
Okay. So let's plot this thing.
Can I ask a question?
Okay?
What are you doing? I don't understand.
I'll show you why why I'm doing this. I want to show you this graph. So this graph represents the information entropy given the probability of getting an apple. So as you can see that the Shannon entropy becomes at the highest, so it becomes highest information when both possibilities share equal amount of probability. So we have flat distribution. So same as previous example when we had 0.25 for A, B, C, and D. That one we have high information. So this one is pretty much similar. The reason I show this is because it's one of the most taught that they use to describe Shannon entropy. And so that you, when you read books, so you know where it comes from, really.
So that means when you have the probability of 0.5 for Apple is when you are seeing more variation.
Yeah, of course, because we have a 0.5.
Yes, and then
for
every time you cannot predict what
Exactly.
might happen.
like let's say here is when you have equal amount of apple
So
and banana in
every
the
sample
bowl.
has information.
Okay.
So,
So if it is apple only, there is no point in looking at it, right?
Yeah.
your plot here, you plotted the entropy. What's your x and y?
Y is the entropy, X is the P.
Probability.
Okay. Okay.
That's the probability
Of apple.
of A. Well, of either because.
So.
Yeah, it could be either.
This question, what is the entropy means?
Entropy is the measure of information that that you gain by by making observation of a particular system repeatedly.
So then is it fair to say that then entropy would be the closest point where you've got near similar probability, well ideally equal probability, or similar probability of
Entropy
holding
is a
up?
measure of uncertainty. I don't want to
Or
say
the
that.
So if you
that's what I wanted to say.
yes or no questions.
Yeah.
Let's say when probability of apple is 1, you don't have to ask any questions, right? So there's 0 questions about it. It's apple, right? And when it is all bananas, like there's no point in asking a question. It is all bananas. But when you have in between, then you have to ask a question. Oh, next one, whether it will be a banana or apple, right?
So we say entropy is the opposite of
The highest
certainty.
uncertainty.
Yeah,
Opposite of certainty,
that's
yes.
why entropy is-
Yeah, if it is certain, there's no entropy.
Exactly.
Meaning there's no point in further sampling that data.
Yeah.
It is settled down.
Yeah.
Right? So in terms of a dynamic system, the transient has more entropy than the steady state.
Yes.
The steady state has no entropy.
Yes.
Right? So in Nantachai's all these experiments, you look at entropy of probing, right? You know, I found a nodule and then that's it, right? There's no point in probing in that tissue.
Yeah.
So that is why we are looking at entropy as a guiding factor.
Which entropy is it that we're looking at? Is it entropy of acquiring new information?
No, the requirement to get new information about a decision, to make a decision.
So it's
So we're looking at the spread of the data and not
It's-
the information.
Yeah.
So it's the entropy of the data.
it's entropy of the data.
Okay.
Yeah.
That determines whether new observation would be meaningful or meaningless.
Meaningful or not.
Oh.
Yeah, it's the opposite of certainty.
Okay. So, so everyone understands.
That is really,
Shannon,
really important. That physical meaning is really important.
Shannon, entropy, any more question? I hope it's quite clear. Okay.
So it will digest when you think about it, all these examples. So it has to slowly digest.
I have one question. So the probability, for example, is fixed. So let's say probability is 0.5.
Mm-hmm.
So I should measure all the time because I have an entropy of 1 because I would gain more information.
Because you have less certainty.
Yeah, that's what I'm saying. So if I have a probability of 0.5, I know that 0.5, I should be checking or
So you have
to have-
every time.
You're half certain, right? So then.
Yeah.
No, it depends, right? It depends on how many possibilities
So
you have.
yeah.
So,
If you have only 2 possibilities, you're getting probability of 0.5. That is like not
Yeah.
uncertain, right?
In the
But however, if you have like million of possibilities, then getting a probability of 0 point something is the maximum entropy already.
Even when you have 2 variables, you're still getting uncertainty of 0.5 because you don't know what's going to be coming out of the machine. on the next.
Exactly. So it like in terms of, it depends on the situation. So let's say we write a grant, and then we know for sure that it is going to get accepted. What is the surprise when you get the letter of acceptance, right?
yeah.
You expected that, right? So there's no happiness or pleasure or anything, right? There's nothing cool about it. And you knew for sure that it's going to get rejected, right? There's nothing, right? So I knew that, right? But if it is 50-50, the tension is highest,
Yeah.
right? You want to wait, you cannot wait, it is 50-50.
But that's
Right.
why I'm saying when the value is 0, is 50-50, it's worth it. to be
It's
waiting.
worth waiting, it is worth the time of, thinking about it. Oh, if there is a tension in for the information, you are looking forward to that information.
Yeah, and I'm just
Right. right?
The word tension used is actually interesting because the more, so, I mean, you could be 100% certain that you're gonna get it,
Yeah.
or, but there is a spectrum over here,
Yeah.
so the more inclined you are towards getting it, the
Yeah.
tension is reducing in both
Yeah,
directions.
in both directions.
Yeah,
Yeah.
till the point of zero tension
Yeah.
at the extreme ends.
No, I want to address that having a probability of 0.5 is not always the case when you have a maximum entropy. It depends on how many possibilities
Exactly.
you
How
have.
many possibilities you can?
It's closer you get to equal probability of
Yeah,
everything happening.
the correct way would be if you have a flat distribution, then that is
That
when
gives
you
the
have high
maximum.
entropy.
Yeah.
Two points. First one is, I think when you get your data, okay, you calculate channel entropy. 8, for instance, is 2 for one set of data, and another is, let's say, 7. What can I conclude from this?
So one has higher information, but you cannot directly correlate.
So I would say the value with higher entropy.
Like for the previous case, we would say that machine one would produce more random variables in the next observation.
Yeah.
Yep.
More information. Okay. Okay.
I'm going to move
And
on to the
unit
next
fits.
topic.
Oh, this is the last one now. Kudak. I will talk about Kudak movement divergence. Do you have time?
I mean, I'm suggesting maybe we could continue this into another session so that we shouldn't.
How long will it take the course activity?
It's quite some time if we want to discuss it in detail.
Depends, right? So but next week we'll be in ICRA.
Yeah,
Yeah.
so the following week we could continue.
Is that?
You want to actually your trial presentation.
All right.
Well, the meeting's earlier, so
So sorry.
we should have time. Or you give your child now?
Now, yeah, because
Oh.
it's only
Yeah.
3 minutes.
Next week there is no group meeting.
Yeah.
Yeah, we are in ICRA.
Yeah, let's do the trial.
So do you
Then
want
after coming back we'll continue.
Yeah.
Okay.
Right? Great, thank you.
Yeah, thanks.
So it really went well. So these fundamentals are really important.